Welcome to this series of videos where we explore how to define and solve electromagnetic problems. This playlist is designed to take you from the foundational concepts of electromagnetism to advanced applications, particularly in the field of brain imaging. In this first video, we lay the groundwork by introducing key mathematical concepts essential for understanding electromagnetics. We will dive into vector analysis and the mathematical formulation of electromagnetic waves, which are crucial for grasping how electric and magnetic fields interact and propagate. We'll explore the following topics: vector fields and linear algebra, how they form the backbone of electromagnetic theory; Maxwell's equations, an introduction to the differential and integral forms that govern electromagnetic phenomena; electromagnetic wave formulation, the basics of how waves are mathematically described and how they propagate through space. This foundation will prepare you for the upcoming videos, where we'll discuss the radiation of electromagnetic waves, their propagation through different materials, and apply these principles to real-world problems, including brain tissue analysis and imaging. To delve into computational electromagnetics, we begin with Maxwell's equations. These equations form the foundation of electromagnetic theory and consist of four fundamental equations, which are represented on the left side of this slide in both differential and integral forms. Their concepts are also visualized schematically. Maxwell's equations are: 1. Gauss's law for electricity describes the distribution of electric charge and the resulting electric field. 2. Gauss's law for magnetism states that there are no magnetic monopoles, hence, magnetic field lines are closed loops. 3. Faraday's law of induction indicates that a changing magnetic field induces an electric field. 4. Ampere's law, with Maxwell's addition, relates the magnetic field to the electric current and changing electric fields. From these four equations, we can derive the nature of time-varying vector fields and electromagnetic waves. Specifically, Maxwell's equations show how electric and magnetic fields propagate as electromagnetic waves. These equations consist of two related to electric fields and two related to magnetic fields. To fully understand these phenomena, we will explore vector analysis and the fundamental principles of electromagnetic waves as time-varying vector functions from a mathematical perspective. This includes deriving wave equations, such as the hyperbolic wave equation, and understanding Poisson's equation in the context of electromagnetism. By analyzing these equations, we gain insights into how electromagnetic waves propagate, interact, and how they can be modeled mathematically. Vector fields and linear algebra are indispensable tools for understanding and solving problems related to electromagnetic phenomena, particularly through the application of Maxwell's equations. These mathematical concepts allow for a deeper comprehension of how electric and magnetic fields behave across various physical situations. Vector fields are fundamental in electromagnetism, representing the distribution of vector quantities, such as electric and magnetic fields, across space. These fields are analyzed using key vector calculus operations: gradient, divergence, and curl. The gradient measures the rate of change in a scalar field, like electric potential. The divergence identifies sources or sinks within a vector field, such as charge distributions generating electric fields. The curl describes rotational properties within a vector field, crucial for understanding magnetic fields generated by moving charges or currents. These operations form the backbone of Maxwell's equations, which are typically expressed using vector calculus notation. These equations govern electromagnetic theory, describing how electric and magnetic fields propagate and interact. On the right-hand side of the slide, figures illustrate fundamental vector operations: unit vectors, dot product, and cross product. The dot product helps us understand the projection of one vector onto another, which is essential for analyzing fields like electric fields in specific directions. The cross product results in a vector perpendicular to the original two vectors, crucial for understanding phenomena like magnetic force and torque. Linear algebra plays a significant role in electromagnetism by providing the framework for solving the complex systems of equations arising from Maxwell's equations. Concepts like matrix operations, eigenvalues, and eigenvectors are particularly useful in more complex scenarios, such as analyzing electromagnetic fields in anisotropic media or solving boundary value problems. Together, these mathematical tools, vector calculus and linear algebra, allow us to model, understand, and solve real-world electromagnetic problems effectively. They enable a detailed analysis of how electric and magnetic fields are distributed, how they interact, and how they propagate through space, providing the foundation for much of modern electromagnetic theory. In this slide, we delve into the fundamental operations of vector calculus, gradient, divergence, and curl, within a vector field, exploring how these operations help us interpret the behavior of fields. Additionally, we will introduce the Helmholtz decomposition, a powerful theorem that breaks down any sufficiently smooth vector field into three distinct components. The gradient of a scalar field points in the direction of the greatest rate of increase. A zero gradient indicates no change in field intensity, a positive gradient signals an increase, and a negative gradient marks a decrease. Visualizing these scenarios, imagine a flat plateau where the scalar field, such as electric potential, is uniform. This represents a zero gradient. A hill where the field increases as you move up illustrates a positive gradient, while a valley, where the field decreases as you move down, represents a negative gradient. The divergence measures how much a vector field spreads out or converges at a point. A zero divergence implies no net outflow or inflow, a positive divergence suggests a source where the field is spreading out, and a negative divergence indicates a sink where the field is converging inward. For example, visualize a uniform fluid flow where the same amount flows in and out at any given point. This shows zero divergence. Air being blown out of a fan, where field lines radiate outward, represents positive divergence, while water draining into a sink, where field lines converge, illustrates negative divergence. The curl represents the rotational tendency of the field around a point. A zero curl indicates no rotation, while a positive curl signifies counterclockwise rotation, and a negative curl indicates clockwise rotation. To visualize, consider a calm river flowing straight with no swirls, representing zero curl. A whirlpool spinning counterclockwise demonstrates a positive curl, whereas a whirlpool spinning clockwise shows a negative curl. These operations are interconnected through key mathematical relationships. The curl of the gradient of any scalar field is always zero, meaning that there is no rotational component in the direction of the steepest ascent or descent. Similarly, the divergence of the curl of any vector field is zero, indicating that a purely rotational field has no net source or sink. The divergence of the gradient of a scalar field result in the Laplacian, an operator that quantifies the rate at which a quantity diffuses or spreads out from a point in space. The Laplacian is crucial in understanding many physical processes, including the propagation of electromagnetic waves. Finally, the Helmholtz decomposition theorem states that any sufficiently smooth vector field can be decomposed into three components: a gradient field, irrotational component, that is curl-free and associated with the scalar potential of the field, a curl field, solenoidal component, that is divergence-free and associated with the vector potential, and a harmonic component that is both divergence-free and curl-free. This harmonic component represents a field that neither originates from a source nor has rotational tendencies, often linked to boundary conditions or external constraints. Understanding these operations and their decomposition is crucial in electromagnetics, as it allows us to break down complex vector fields into simpler, more manageable components. By analyzing these components individually, particularly in the context of electromagnetic fields, we can better understand and solve complex problems involving the interactions of electric and magnetic fields in space. In this slide, we explore the foundational theorems in vector calculus, Green's theorem, Stokes' theorem, and the divergence theorem, and their applications to line, surface, and volume integrals of vector fields. These theorems provide essential tools for understanding and solving complex problems in electromagnetics and other fields by relating different types of integrals. Green's theorem is a general theorem in vector calculus that relates a line integral around a simple closed curve to a double integral over the region enclosed by the curve. This theorem has two forms. First form, circulation form. This form connects the line integral of a vector field around a closed curve to the integral of the curl of the field over the area enclosed by the curve. It states that the circulation of the vector field around the boundary is equal to the sum of the rotational effects, curl, over the region. Second form, flux form. This form relates the line integral of the field's normal component along the boundary curve to the integral of the divergence of the field over the enclosed region. It tells us that the total flux through the boundary curve is equal to the net source or sink, divergence, within the region. Stokes' theorem is a specific case of Green's theorem applied to a surface in three dimensions. It relates the surface integral of the curl of a vector field over a surface to the line integral of the vector field around the boundary of that surface. Essentially, Stokes' theorem simplifies the evaluation of surface integrals by converting them into line integrals around the surface's boundary. This theorem is crucial for analyzing magnetic fields and circulation effects in three-dimensional space. The divergence theorem, also known as Gauss's theorem, connects the flux of a vector field through a closed surface to the volume integral of the divergence of the field within the enclosed volume. It asserts that the total outward flux through a closed surface equals the sum of all sources or sinks, divergence, within the volume. This theorem is particularly useful in electromagnetics for calculating quantities like total charge or mass by analyzing the field's behavior on the surface and within the volume. Integrals in vector calculus are deeply interconnected. The line integral evaluates the vector field along a curve, capturing quantities like circulation. The surface integral measures the flux of the vector field through a surface, essential for applying Stokes and Green's theorems. The volume integral calculates quantities like total charge within a volume, relevant for applying the divergence theorem. Green's theorem, in its general form, encompasses both the circulation and flux forms, with Stokes' theorem being a special case that extends this idea into 3 dimensions. The divergence theorem bridges surface and volume integrals, showing how flux through a surface relates to divergence within the volume. By understanding these relationships and their integral forms, we can effectively use these theorems to simplify and solve complex vector field problems, gaining deeper insights into the behavior of electric and magnetic fields and their interactions in various physical scenarios. In this section, we'll explore the fundamental role of boundary conditions in electromagnetics, which are essential for understanding how electromagnetic fields interact with surfaces and interfaces between different media. These boundary conditions are not just theoretical. They are directly derived from Maxwell's equations, the cornerstone of electromagnetic theory. By carefully applying Maxwell's equations at the interfaces between different materials, we can extract the specific boundary conditions that the electric and magnetic fields must satisfy. This process ensures that the fields behave correctly at the boundaries, a crucial aspect when solving real-world electromagnetic problems. One key boundary condition is the continuity of the tangential components of both the electric and magnetic fields. At the boundary between 2 different media, these tangential components must remain continuous. This means that the parts of the fields parallel to the boundary cannot undergo sudden changes, which ensures that the electromagnetic fields transition smoothly from one medium to another. This smooth transition prevents any unrealistic discontinuities in the behavior of the fields. On the other hand, the normal components, the parts of the fields perpendicular to the boundary, can experience discontinuities. These discontinuities are related to surface charge and surface current densities. For instance, the normal component of the electric displacement field may jump by an amount proportional to the surface charge density at the boundary. Similarly, the normal component of the magnetic flux density can be influenced by surface currents, causing a discontinuity. To help visualize these concepts, we've included figures illustrating different scenarios of boundary conditions. These images will show how the fields behave at boundaries under various conditions, such as when transitioning from a conductive material to a dielectric, or when encountering surface charges and currents. By seeing these examples, you'll better understand how to apply boundary conditions in practical situations. Grasping these boundary conditions is essential for accurately modeling and analyzing the interactions of electromagnetic waves with various materials and interfaces. Whether you're designing antennas, waveguides, or studying how electromagnetic fields propagate through complex media, mastering these conditions will ensure that your solutions are both accurate and physically meaningful. Now that we've covered the fundamental boundary conditions, let's move on to a critical concept in electromagnetics, the uniqueness theorem and the duality of electromagnetic fields. On the left side of the slide, we see the uniqueness theorem, which states that if the boundary conditions and sources of an electromagnetic problem are well defined and satisfy Maxwell's equations, the solution to the fields within the region is unique. This is a powerful result because it assures us that the fields we calculate, given the correct boundary conditions, are the only possible solution for that scenario. The reliability of our solutions in complex electromagnetic problems, such as those involving antennas, waveguides, or imaging, is guaranteed by this theorem. Directly tied to this is the concept of duality in electromagnetics. Duality refers to the symmetry between electric and magnetic fields in Maxwell's equations. For every electric field scenario, there's an analogous magnetic field scenario. This symmetry simplifies the analysis of complex problems, as it allows us to switch between electric and magnetic perspectives depending on which is more convenient for the problem at hand. On the right side of the slide, you'll notice a schematic illustrating this duality through 2 examples: the image theorem for a perfect electric conductor and the equivalent model for a magnetic source near a conductor. The image theorem, shown here, demonstrates how the fields generated by a real source can be replaced by an imaginary or image source inside a perfect conductor, allowing us to simplify the problem while maintaining the correct boundary conditions. Similarly, the equivalent model illustrates how a magnetic source near a conductor can be modeled using equivalent electric sources to simplify the problem. These examples highlight the practical application of the uniqueness theorem and boundary conditions. By ensuring that we define our boundary conditions correctly, we can confidently use these models and theorems to solve complex electromagnetic problems. Whether we're dealing with electric or magnetic fields, or applying the image theorem to simplify a situation, the uniqueness of our solution is guaranteed as long as our initial conditions and boundaries are well defined. As we conclude this session, let's explore some important equivalence principles in electromagnetics, illustrated here on this slide. On the left, we see an illustration of the surface equivalence principle. In this scenario, we have an imaginary closed surface with impressed electric and magnetic current sources, represented as Js and Ms in the original problem, shown in part A. We have the true source distributions inside the surface, denoted by J1 and M1. The equivalent problem, depicted in part B, shows how these sources can be replaced with equivalent sources on the surface S. This replacement yields the same external electric and magnetic fields as the original problem, while the internal fields and surface currents are adjusted to enforce the correct boundary conditions. This principle is essential in simplifying complex field problems, reducing them to surface integrals without altering the external field distribution. On the right, we have an illustration of Love and Shelkonov's equivalence principles. Starting with part A, we have the original problem. Part B shows Love's equivalent problem, where the fields inside the region are replaced with equivalent surface sources, ensuring that the external fields remain unchanged while the internal fields are adjusted. Parts C and D show Shelkonov's equivalent problems, part C with a perfect electric conductor and part D with a perfect magnetic conductor. In both cases, the external fields remain the same as in the original problem, but the internal sources and boundary conditions are chosen to match the physical constraints of the conductors. These illustrations clearly demonstrate how the equivalence principles allow us to transform complex electromagnetic problems into more manageable forms without altering the external field behavior. By understanding and applying these principles, we can greatly simplify the analysis and design of electromagnetic systems, especially in antenna theory and waveguide design. With this, we bring today's video to a close. In the next session, we will build upon these concepts by exploring the principles of electromagnetic radiation and propagation, diving deeper into how these equivalence principles can be applied in practical scenarios. Thank you for watching, and I look forward to seeing you in the next video.